We have Pelican Systems. They designed a small unmanned air system, again, not so small in terms of wingspan, but they had a high endurance requirement also for a Coast Guard mission. So I'm going to turn it over to Grace Brennan, and she'll take it over. She's their team leader.
Thank you. Like I said, my name is Grace Brennan. I'm the detailed team lead for Pelican Systems, and here's the rest of my team. We have Jacob Heilman, Phil Rick, Alex Matamoras, Stephen Hawkins, Bryce Libertone, Salvador Cardenas, Timber Aguilar, Alex Keel, and Hannah Warren. So our design goals for the semester started with our wind tunnel testing, which first we had to finish, we added some carbon fiber to the wind tunnel model that was created last semester to enforce it. And we did that to check our values that we came up with during the preliminary design process. After that was done, we started our loads predictions to determine the loads that would be, or predict the loads that would be applied during flight. We were also doing material selection and testing to determine the material properties of both carbon fiber and e-glass. Those values were then used in our structural analysis along with the loads predictions to make sure that our structural configuration could withstand the loads that would be applied. After we finished all our structural analysis, we began the drawing package, which also meant that we could start our manufacturing of the structural test article, which included the fuselage and the wings. We then went into structural testing, which we applied load to the wings, just as the Louvetar did. And then once that was complete and we finished up the rest of our aircraft. Finally, the plan was to taxi test and flight test, but unfortunately due to CG complications, we're only able to do our taxi tests. This we'll go into further. Hannah Warren will talk about it. Additionally, our aircraft is unique because we have an EE member on our team, and he created a autopilot system for our aircraft. And the plan for that was to do some bench testing on the ground and then actually have it fly the plane if we had been able to flight test. However, we'll still do the bench testing. Here are some of our mission requirements. For our original preliminary design, we actually created an aircraft that would be both land-based and sea-based by creating two separate landing gears, one with wheels and then one with pontoons. However, for the detailed process, it was decided that we would create just the land-based version of our aircraft. Here's our Seabird. Some differences, we took some cutouts in the vertical tails. Our booms got a lot thicker and the nose gear went up a little bit. It's not really, you can't really see on there, but here's some of our dimensions. We have a wingspan of 12.5 feet. We used a GOE 398 airfoil, and we have an aspect ratio of 9.2. And now Jacob Heilman will talk about wind tunnel testing.
Thank you, Grace. I'll be discussing the wind tunnel testing that we conducted in the beginning of the semester. We conducted wind tunnel testing in accordance with our wind tunnel test plan, which was developed in the preliminary design phase of the project. We used the wind tunnel testing to perform to evaluate the aerodynamic and stability predictions completed in the preliminary design phase of the project. And I'll be going over a brief summary, and I'll be going over the results we had from the testing. All right, so here's our wind tunnel model. It's shown up here, and also we have it right here. We use a 3D printer to get the 3D aerodynamic profile. Then we use a steel substructure to use for the booms and to place in the wing, and it uses as a mount, which will help make the model more rigid. We also place uni-axial carbon fiber on the top and bottom surfaces of the wing. We did this to increase flexure and have it be more in accordance with our predicted model. We also conducted testing with the landing gear off, because during testing we found out it was causing a parasitic drag of over 10%, and as per Dr. Traub's recommendations, we removed it. We used a closed circuit subsonic wind tunnel with a 6-component pure metal balance with a lab new code. We conducted an AOA sweep with the tail on, tail off. a beta sweep with the tail on, tail off. We also did flow visualization. One thing I'd like to note here is initially, for both tests, we had erratic drag data. So we had to reconduct testing. Unfortunately, we're only able to do this with our tail on, since the tail is epoxied in. And you'll see this in the drag polar and plots following that. All right, so here's our lift curve slope. As you can show here, we have an increased CL max than are predicted, but we also install a lower angle of attack. We also have an increased lift curve slope, which will, as shown here, which also will allow us to loiter at a loiter and cruise at a lower angle of attack. Here's a drag polar. As shown here, we have less drag than predicted. And you can see how the erratic data shown with the tail off. There, originally the tail on had that too. When is our predicted model, we revised our predicted model from the preliminary design phase, and we removed the landing gear to compare apples to apples. And we had increased span efficiency than our predicted. Our CM versus AOA, it shows we have an alpha trim at 4.5 degrees. That'll be quite important in the following slides. And we have close to predicted pitching moment derivative, which means that we'll be stable, we'll return to zero AOA when we stall. Here's our range. Here's our range plot. Our LVD max has increased with the increased lift and a decreased drag. As you can see here, we originally had a erratic nature with the tail on as well, as shown here. This is due to the drag. This is for the tail off. And we use the Brigaday range equations to reevaluate our predicted range. And this was using a battery that was done in the power requirements analysis in the preliminary design phase of the project. So it was a larger battery with a higher energy density. Here's our endurance plot. And as shown here, we have an increased endurance than predicted, which also occurs at 4 degrees angle of attack. And as I didn't say here, we also, our maximum range condition, or maximum L over D occurs at angle of attack of 4 degrees. So not only will we be flying naturally at 4 degrees, we'll be also flying at our maximum range and endurance conditions. We also reevaluated our predicted endurance during the loiter phase, and this once again was used with the power, in accordance with the power requirements analysis, battery calculations. Here's our static margin. So as you can see here, we have a slightly decreased static margin, but we're still close to the 10%. So we're stable, but yet we are still maneuverable. Here's a directional stability derivative. As shown here, it is slightly increased than our predicted. And what that means is, as wind increases with increasing beta, our aircraft will naturally tend towards the wind direction. It'll towards the wind. Here's our lateral stability derivative, as shown here. It's significantly larger than predicted. So that means we're stable in roll. I would also like to point out a discrepancy here. We're supposed to at 0 beta, it should be 0. So right now it's showing a small rolling moment. And why that is because since the value is so small, as you can see here, that is accounted for in model asymmetry during the manufacturing process. Here's a flow visualization test where we used an AOA sweep, and we attached tufts with tape to see how the flow would behave during stall. We also attached string to the end of each wing, and as you can see here, the large wingtip vortices that are created. So in conclusion, our biggest discrepancies from our predictions in the preliminary design phase was our lateral stability derivative. So next, and this data will be used to develop the load predictions of our project, and which will later be used for structural sizing. Next is Philip Reich with load predictions.
Thank you, Jacob. Good afternoon, everyone. I'll be talking to you today about load predictions. To do this, we first started off with a VN diagram with the gust velocities. We then calculated the load distribution, the shear diagrams and moment diagrams for the wing, empennage, and the fuselage, as well as developed the critical loading for the landing gear. First, we developed a VN diagram. We did this to develop the full range of airspeeds and load conditions, G loads that the aircraft can handle. As you can see here, we have our positive stall line right here. Our negative stall line here shown in red. Then we have our airspeeds. Our stall airspeed is about 20 knots. Our maneuver airspeed is about 30 knots. Our cruise condition is around 43 knots, and our dive speed is about 61 knots. We also developed our loading, max G loading from the CFR Part 23. As shown, the positive is 4.5 Gs, with our negative being negative 1.79. We also had our RFP requirement that the max G loading that the aircraft could take would be 2.5 Gs, so this is later evaluated. We developed these gust velocities as shown. These are the rough air cruise and dive velocities. As you can see, they're a bit limited. The second line shown here, I know this is right here, about 2.5 Gs is our max G loading. So therefore, the gust velocities defined from CFR Part 23 is a little bit limited according to UAS due to lack of UAS regulations at this time. We then developed a full VN diagram. We basically modified our gust velocities to be at the max of our cruise and dive, as shown in the green and blue lines. The velocities that correspond here are the max crosswind component that the aircraft can handle at these cruise and dive velocities. We then developed our full VN diagram as shown here, the blue lines, with the max being at the V dive, as shown here, with the max positive and negative load factors, as shown. Then, next job was to develop our critical loading condition, to define all loads on the aircraft. We analyzed two conditions here, at the main point as shown here, and then the highest airspeed at the V dive. After analyzing both, we realized that the condition as shown here gave us the highest CL max, which provided a better loading condition than at an airspeed. We checked out the trim conditions of the aircraft and found that the aircraft loading condition produces a higher loading than the one at the higher speed. This was then passed off to determine our wing loading. We determined the wing loading to determine the ultimate loading of the aircraft, as well as pass this on to wing sizing to determine the proper sizing of all the structural components of the wing. We did a sum of forces calculation based off the leading edge of the aircraft, as shown here, the axis system. The blue forces are shown as lift forces, and the green forces are shown as drag forces, as shown here. The lift, we also took into a lift of the tail, as defined from Jacob Hallman's section. We took tail-on testing in the wind tunnel section. We then took the load distribution via Streck's approximation across the loading of the wing. It varies from about 0.7 to about 0.2 at the wingtip across the 75-inch half span. This also produces shear across the half span and moments as seen here in the Y direction, as well as in the X direction. We integrated Streck's approximation across the wing to come up with a shear diagram. As shown here, the winger location at 3.25 inches has a shear of about 52 pounds. We also have a discontinuity because the tail has a load being transferred through the spar through both the forward and aft spar of the wing. As you can see here, here's a discontinuity of about 15 inch-pounds at the winger location of 12.575 inches aft span-wise of the cord. We also integrated that to get our moment diagram, as shown here. It's about 1,300 inch-pounds. This is our critical moment condition of the wing, also at 3.25 inches span-wise of the center line of the aircraft. We also developed a torque of the aircraft is significantly less than the bending moment of the aircraft, being about 288 inch-pounds at the same location. The discontinuity of the tail also causes a discontinuity of about 90 inch-pounds at the location where the tail boom attaches to the wing. We also did a chord-wise pressure distribution across the wing. The red shows the upper pressure distribution, where the blue shows the lower. We took the difference to find the total pressure distribution, integrated, and came up with the center of pressure at about 44% of the chord length. This was then defined in wing loading sizing section to determine which percentage is applied to the forward spar and which is applied to the aft spar. Moving on to empennage loads, we took the center sum of forces and moments about the axis of the aircraft, similar to the wing. We took it about this forward edge of the horizontal tail as shown, with the same axis system. We then, as talked about before, we took the tail-on testing and determined the load that would be applied at the tail of 6.26 pounds. We also determined that the load determined through the deflection of the elevator, which adds an additional 1 pound to that load. For the vertical tail, we determined that the load is about 0.5 pound with the deflection of, not deflection of the rudder, but for the loading of the tail. This is all taken at 31 knots equivalent airspeed. We then applied Streck's approximation across the half span. As you can see, it's symmetrical as predicted. It varies from the right side of the aircraft, as shown here, to the left side of the aircraft, to the horizontal tail. We integrated that again to come up with our shear diagram, varying from negative 3.2 pounds to about 3.2 at the span of the spar. We then integrated that again to get our critical moment on the horizontal tail of 1.8 foot-pounds. Moving on to the vertical tail, we took traction approximation again to cross the vertical tail. This is from the root of the vertical tail all the way up to the top 13 inches to the top of the vertical tail. And as you see, it goes from 1.8 to about 0.4 at the top of the vertical tail. Integrating, we develop our vertical tail shear diagram, about 2.1 pounds. It's our critical for the tail. And for the moment diagram, about 13 pounds for our moment inch pounds. The empennage loads were also provided to give into the empennage sizing section to determine the proper sizing of the empennage section. We also developed the fuselage loads based off center of gravity, the shear, lift, shear, and moment diagrams, as well as the critical landing conditions for each landing gear. We took our center of gravity with that equation there, our shear, our lift, shear, and moment diagrams from these, and our ultimate loading conditions for the landing gear as shown here. To find the center of gravity, we removed the payload that we initially had from the initial preliminary design configuration. We added less batteries and added some ballast in its place, and we iterated so we came up with a CG that was the same of our 18.7 inches after the forward of the nose of the aircraft. We then estimated the lift distribution on the tail via cantilever beam. As you see here, the lift of the horizontal tail is estimated here, with the forward and aft spars shown here, with the reactions shown here. We then integrated to come up with our shear diagram. This is from the forward of the nose, aft. As you see, here's the location of the forward spar and the aftward spar. Significantly higher for the forward spar, about 160 pounds for the load applied to the forward spar. For the moment diagram, we integrated again to come up with a forward station on our, the moment on our forward spar, about negative 650 inch-pounds on our aft spar. We then analyzed our critical loading condition based off CFR Part 23. We used a weight of 25 pounds with our max NZ with 2.67. We then assumed that the load taken on each landing gear was applied to one landing gear, say like a bad landing was applied solely to a landing gear to come up with our entire critical loading condition of 83.5 pounds for the landing gear. Here's a summary of all the critical load conditions. As mentioned, these were passed on to the sizing section to determine the proper sizing of all the proper components of the wing, fuselage, empennage, and the landing gear. I'll now pass it off to Alexander Motomores to talk about our material testing.
Good afternoon. Today I'll be going over our material testing. We needed to obtain material properties for structural analyses and also going to go over the tests we performed to obtain these properties. So we needed material properties for initial structural sizing as well as ANSYS structural analysis. And we had e-glass and carbon fiber wet layups using a quasi-isotropic layup. And the reason we use a quasi-iso layup was so that we could use solid mechanics theory to do our analyses. And also, these materials are representative of what was used in the structural test article and the flight test article. Our first test was tension testing using 1.5 inch by 10 inch coupons, and we obtained Young's modulus and ultimate tensile strength from these tests. We used a large tensile tester in the machine shop, and we tested 5 coupons for each material. The coupons are right there. So here are results for our e-glass. We obtained the Young's modulus by averaging the slopes of each curve. And we obtained the ultimate strength by averaging the point at which each curve ends, so failure of each coupon. And this vertical line corresponds to where the extensometer was removed. And we followed the same analysis with the carbon fiber coupon results. And for Poisson testing, we used a similar tension test setup, except we mounted strain gauges in the lateral direction and the axial direction. And we used a smaller load frame for this. The load was applied in increments using the jog feature of the tension tester, and we used a portable strain indicator to measure the strain on the coupon. Now here's our results for the e-glass. Unfortunately, one of our coupons had different strain gauges, so that's why there's only one curve. And we used the linear portion of the curve to obtain this Poisson ratio. Now, we think this portion here that is not linear because the coupon was adjusting itself in the load frame. And we followed the same analysis with the carbon fiber, except this bottom curve ends prematurely because our coupon actually fractured in the test. Now for shear testing, we used the 3-rail setup with a compression attachment on the load frame. And one of the biggest issues we ran into here was that this middle rail would move down, it would shear through the coupon, and it's shown here. And we obtained ultimate shear strength from these tests. And we obtained the ultimate shear strength by taking the first drop in load where that occurred. And we averaged the results from our 3 runs. And we followed the same method for carbon fiber. And in conclusion, here are our material properties we obtained. These values, the plus minus, correspond to the scattered data, it's the standard deviation. And it's important to note that in our flight test article, we also used the pink insulation foam, but we weren't able to test that properly, so we used published data for that. And next is Stephen Hawking with structural configuration.
Thank you, Alex. After we obtained the material properties from the materials testing, we moved forward and configured the structural components within the system. We configured the wing, empennage, and fuselage. The wing is made out of carbon fiber for strength. The empennage is made out of e-glass because it's lightly loaded. And the fuselage is also made out of e-glass for transmittivity between the onboard computer and the ground station. This image shows the overall structural configuration of the system with the wing, ribs, and spars, the empennage, ribs, and spars, the tail booms, the fuselage bulkheads and longerons, along with the floor, the firewall, and the landing gear. The first component we configured was the wing. There are 2 spars and 23 ribs, 12 ribs on each side, with the center rib being shared between the two sides of the wing, the left and right sides. This image also shows the center wing portion, which is connected to the fuselage, and the 2 outboard portions, which can be disassembled from the center wing portion. The disassembly is due to the requirements from preliminary design to fit inside a 3-foot by 3-foot by 6-foot box, and it also allows for easier transportation of the structural test and flight test articles. This shows the right side of the wing cut off at the center line of the wing. The ribs were placed on either side of the aileron, the wing tip, the wing root. There was also a rib placed on either side of where the sail booms connect to the wing, and also a rib on either side of the disassembly location, along with a few extra ribs spaced it out just for additional strength and to help keep the airfoil shape. After we configured the internal structure of the wing, we moved forward and configured the empennage in a similar manner. The horizontal tail has 1 spar and 3 ribs. The vertical tail also has 1 spar, but it only has 2 ribs. For the horizontal tail, you can see the spar running across the span with a rib on either end, along with a rib in the center. On here, you can also see the size of the elevator compared to the overall size of the horizontal tail. And the size of the elevator is due to the requirements from preliminary design to take off from a gravel runway. We needed a very large elevator to be able to rotate on the gravel runway because of the high coefficient of friction. For the vertical tail, we have the spar sitting vertically, and this was for ease of manufacturing, so we wouldn't have to drill holes at any strange angles when we were building the vertical tail. There's a rib on the tip, 1 at the root, and the rudder. And as you can see in the rudder, there's a cutout section. This cutout is to allow for both elevator and rudder deflection at the same time. This image shows the final configuration of the empennage as it would be assembled, where the horizontal and vertical tail spars attach to the tail booms, which would then be attached into the wings. After we configured the empennage, we configured the fuselage with the bulkheads, longerons, floor, firewall, and the wing supports. This image over here shows the fuselage with the skin and landing gear attached. This is the basic shape of the bulkhead. There's a slot on each side, and that is to allow for connection with the longerons. This is the basic shape throughout all of them, except the bulkheads that are underneath the wing have an additional slot on each side of the top bulkhead, and this is to allow for the additional wing supports to be attached to the bulkheads. The bulkheads are made out of e-glass and foam sandwiches, similar to what we have here, except there's less foam, it's only 0.2 inches of foam. After we configured the bulkheads, we moved forward and put them in the fuselage. We have a bulkhead on either side of both the forward and the nose and main landing gear. A bulkhead on either side of both the forward and aft spar, one at the leading edge of the wing, one at the trailing edge of the wing, and one at both the front and rear ends of the main fuselage section, along with the firewall at the aft of the fuselage, which is where the engine is mounted. After we created the bulkheads, we created the longerons. The left and right longerons are e-glass and foam sandwiches, similar to the bulkheads. The top longeron includes an angled section in the back, which is where it connects to the firewall for engine mounting. It also includes a portion in the middle that has the profile of the wing airfoil, which is the GOE-398, and this is because this is where the wing attaches to the fuselage. The additional wing supports that go on either side of the top longeron include the shape of the airfoil and also the holes for the forward and aft spars. Again, this is because this is where the wing attaches to the fuselage. The bottom longeron includes an angled section for the fuselage upsweep, which is included in the design to allow for enough rotation for takeoff. It also includes a cut in the middle, and this is for mounting of the main landing gear. The cut is there so we can mount the main landing gear directly to the floor of the fuselage. The other fuselage components that we needed to take into consideration was the skin, which is 2 plies of e-glass, and the skin is considered a non-structural component. The floor, which is 4 layers of e-glass, and this is where all of the internal components such as the batteries, the computers, and the landing gear are mounted to, and the firewall, which is a 1/4 inch of plywood, and this is where the engine is mounted to, and it's, again, in the aft of the fuselage. And it's plywood to act as a fire block in case something were to happen to an engine, and to also allow for enough support for us to screw the engine into. After we configured, so in conclusion, the ribs and longerons were placed at key locations throughout the wing and empennage. There are 2 carbon fiber spars in the wing, 1 in each surface of the tail, and the carbon fiber spars are made from pre-manufactured carbon fiber tubes that we bought from Clearwater Composites. The bulkheads were placed at key locations throughout the fuselage, and there are 4 longerons within the fuselage. After we configured the structural components of the system, we moved forward and sized the structural components of the system. Here's Bryce Liverton with structural sizing.
Thanks, Steve. So I will be going over how the wing was sized, the empennage was sized, and the fuselage was sized. For the wing sizing, we sized the spar to bending and shear stress. The ribs were sized to shear flow, and the skin was sized to shear. For the spar sizing, we have the forward and aft spar here with the diameters and the thickness. For the bending, we used the bending equation and the moment of inertia equation, given the ultimate force by the manufacturer of the carbon fiber and the ultimate moment given by the load section. We were able to determine a thickness for each of the forward and aft spar. After bending, we moved to shear. Use the shear equation up here with the just found thickness that we found for bending, and applied it to the equation so we can come up with our ultimate shear, and compared it with the ultimate force of that shear and found that we were well below our ultimate shear stress. After the spars, we moved to the rib. Here we have the GOE-398 airfoil rib with the holes designed to the spars, to the forward and aft spar. The rib thickness was found using a wing box. We used the shear flow equation and the shear equation given the forces from the forward and aft spar. We found our thicknesses desired for each sides of the wing box, and then we used the highest thickness for that we found. For the skin sizing, we have the overall layout of what the skin will look like from the top view of the wing. We use the shear thickness here. Given the ultimate shear and the ultimate moment, we found our thickness labeled here. We then applied it to the equation and found our ultimate shear that we will be experiencing in our top wing and our lower wing, and then compared it to our ultimate shear and found that we are again well below and will not shear. For our final wing sizes, we have all of our calculated values located right here. Next to that, we have our standard sizes that we will be using because we do not want to make custom parts for our plane. It was much easier just to buy them. For our empennage sizing, we did the exact same thing. We sized our spars to bending and shear stress, our ribs to our shear flow, and our skin to our shear. For our bending sizes, or bending moments, we have the ultimate force given by the manufacturer. We have our maximum moments that we will be experiencing given by our load section, and we found our thicknesses down here with the equations mentioned before in the wing section. For the moments of inertia, we first assumed a thin wall, and then we used the inner and outer diameter to find our regular moment of inertia located here. Our spar shear, we used the maximum force here and found our maximum shear that we will be experiencing, then compared it to the ultimate shear of the material, and once again found that we were well below. For our skin thickness, we used the loads for our horizontal and vertical tail to define our thickness that we will be using for our 2-ply E-glass. For our rib thickness, we used the ultimate shear here, and with the ultimate force there, and again, using the equation previously stated for the wing, we were able to come up with our minimum thickness here. For our empennage, these are all of our calculated values for our spar, our skin thickness. And once again, these are all the standard values that we're closely related that we will be using, but we do not want to make all of our parts ourselves. For the fuselage, we designed the bulkheads due to shear stress and designed the longerons to the bending stress. For the bulkheads, we had the outer radius of 3.5 inches and our inner radius of 2.72 inches. Using the shear equation here, we were able to find a minimum thickness of 0.258, which will include our foam inserts. For the longerons, we used the bending equation here with the moment of inertia. With the given width of 2.5, we were able to calculate a minimum thickness of 0.5, which also includes the inner foam. In conclusion, all of our calculated values, or all of our standard values, will not shear as we will not fail as we predicted. Next is the full model with the skin on and how we predicted it would look. Next we have Salvador Cardenas with fastening joints.
Thank you, Bryce. So I'll be going over the fasten joints analysis of our project. So first we had to size the fasteners and bolts for all the landing gear, the nose landing gear and the main landing gear. And as previously mentioned in Phil Rick's section on loads, we're using CFR guidelines with 2.67 Gs and the factor safety of 1.23 or 1.25, and assuming a horizontal loading. And then here you can see a screenshot of our nose gear, which you can also see on the model. This is a threaded steel rod that is used to attach the actual nose gear to the fuselage. And then here you can see the mounting onto the fuselage floor, which is in yellow, and the two aluminum doublers that on each side and the threaded rod going through. And also there's a bushing here to allow for rotation as our nose gear is steerable. So to size the bolts and the fasteners, We applied a fitting factor since it is only one fastener that attaches it to the floor, and a bearing factor as well. And then we sized the diameter and the thicknesses of the doublers and the rod, and we got 0.0513 inches. And since we want to use standard sizing, we used the closest standard size that was readily available, which is a 1/4 inch for the rod and a 1/16 of an inch for the aluminum doubler. And then we applied the same process for the main landing gear, except we didn't use, and here's another schematic of how it is mounted onto the fuselage floor. And then we have the 2 aluminum doublers and 2 1/4 inch bolts. And then with these, we didn't apply a fitting factor as there are 2 fasteners that attach it to the actual fuselage. And we got a diameter of a 1/4 inch and a 1/16 of an inch for the aluminum doublers. And in conclusion, we calculated the bolt diameters, the plate thicknesses used to mount the landing gear onto the fuselage. And next, I'll be going over the ANSYS analysis for our wing. So I'll overview the model construction, the meshing, the loads and supports, and the results that ANSYS gave us. So an important note is that we simulated 2 different types of loading schemes. One was a critical load condition, which is about 2.5 Gs and a factor safety of 1.25. And then a limit load, which was done in structural testing, which is 64% of that in 5 load steps. So the actual model is here, and we have the wing skin, which is 2-ply carbon fiber, and the carbon fiber boom tube. And then here is without the skin, and you can see the foam inserts and the wing ribs at each end of the foam inserts. And then the boom spar junction that attaches to the wing spars that are also made out of carbon fiber tubes, purchased from the same manufacturer. And then here are the material properties that we use. So from Alex's section of material properties, we use the Young's Homologous of 4.1 MSI and 1.78 MSI. And then, as he mentioned earlier, the foam is from CS EduPack, as we couldn't get good values for those the Young's Homologous and the Sonic tube. And the carbon fiber tube was obtained from Clearwater Composites, as we did not perform any materials testing on those either. And then here you can see the meshing on the skin, and without the skin, you can see the wing spars and the wing ribs, as well as the boom spar junction in the foam inserts. And then this loading scheme is of the critical loading condition that I mentioned earlier. And you can see we applied the strength approximation that was calculated in Phil Rick's section. And as well, we applied the 3.1 pounds of the tail force, or half, which is half of the actual tail force. And then we applied fixed supports at these 2 center ribs, which Stephen Hawking mentioned attaches to the fuselage, and then a symmetrical constraint on here to simulate the other half of the wing. And then here you can see the critical load scheme and the wing stations, which we calculated earlier in Phil Rick's section. And then using the critical loading condition, this is what we use to determine where to place our strain gauges for the actual structural testing. As you can see, most of our stress and compression occurs here. And this makes sense with the deflection that we have, as it's deflecting in the positive z-axis, which means the top surface would have compression and the bottom surface would have tension. So here is the look. These results show the loading scheme of the structural testing, which as I mentioned earlier, 64% of the limit load. And this is load step 5. And you can see 2.5 inches from rib 7, which is right next to the disassembly point of the wing. And this is where we placed our strain gauges and later compared them to our ANSYS results. And here's the top surface and this negative strain. And then this is rib 7, where we place the rosette gauge, which is 8.5 inches from the leading edge and 1.5 inches from the bottom of the wing, or bottom of the wing rib. And then we plotted the actual strain values from load steps 1 through 5. As you can see, of the front and aft spar. is positive and the top surface is negative. And then we compare these stresses with the wing sizing predictions to see if we are under what the wing sizing predictions we use to size our structural components. And in conclusion, of results showed that we are over-designed. We designed for stiffness and small total deformation and a low shear stress and normal stress. And the critical loading condition results were used to calculate our margins of safety for the spars, the wing skin, the ribs, and the nose gear fasteners. And then here's the equation for margin of safety, which is the ultimate strength over the results that ANSYS gave us. And then here you can see a table of all those values. Here's the material properties and the ANSYS results. And then our margins of safety. As you can see, our wing spars are really over-designed. And we expected this since we bought those from the manufacturer, and that's what we expected. So in conclusion, all our margins of safety are positive. The wing spars are over-designed for strength, and that's an important note. And then next we have timber argular for structural testing.
So today I'm going to go over the manufacturing of the STA. The STA included the wings and the fuselage only. Then I will talk about the testing procedures and load application that was applied to the STA. And I will talk about the data collection along with the results. And then I will compare the results to the ANSYS. So to start with the manufacturing of the STA, we printed off the drawing package. From the drawing package paper, we glued that to the aluminum and cut out the aluminum using a bandsaw and ground it down to the airfoil shape. For the foam, we used Formular 250. It's a pink insulation foam. We glued the 3 plies together to give us for the shape of the to get the airfoil shape. And then we had to drill holes into the pink insulation foam. We used a cutting jig, as shown in this picture, to keep the drill aligned, and it would come out at this end, and it would come out showing that we are going in a straight line through the pink insulation foam. Once we had the foam cut to the right size and drilled, we put the aluminum templates on the end, and we used a hot wire to cut out the pink insulation foam. For the ribs, we had a 2-ply carbon fiber, as mentioned in Stephen Hawking's sizing section. We again printed out the drawing package and cut out the ribs with a bandsaw. For the spars of the wing, we had pre-manufactured carbon fiber tubes purchased from Clearwater Composite. We placed strain gauges on the spars, and the actual location will be shown in future slides. And then we had the wires of the strain gauges running along the outside of the spars. So with the spars ready, the foam and the ribs, we assemble those all together. Microballoon epoxy and e-glass overlays were used to attach the ribs to the spars that are within the wing. Once we had that all assembled, we applied the skin to the foam and rib sections, as shown in this picture. The skin is e-glass. The skin is carbon fiber, as mentioned in Stephen Hawking's section, and it had a plus minus 45 degree 2 plies. So with the wing, we also had to apply smackling in some areas. This was a lightweight drywall smackle to help smooth out some of the airfoil sections that got messed up with the hot wire. And then we have the boom receptacles as shown here. These had the spars actually ran through the boom receptacles to keep them into place. And we also had to do some sanding to help with the airfoil shape. So with the wings manufactured, we move on to the fuselage. We made a foam cylinder, shown here from an 8-inch by 8-inch by 52-inch foam piece. We used a hot wire to make cut into the cylinder. We then laid up the skin on the cylinder, and we vacuum sealed it to get all the air out of the carbon to the e-glass layup. Once the layup was cured overnight, we made a cut along here and pulled it off. For the bulkheads, we made a flat sheet of E-glass. It had a plus minus 45 degree layup schedule and 2 plies. We placed the large sheet in the water jet cutter, and the water jet cutter cut out all of our bulkheads. We also, the bulkheads are foam sandwiches, as mentioned in this kind of configuration section. And they have a 0.2 thickness of foam within them, and it can be seen better in the coming up slides. For the longerons, they were manufactured the same way as the bulkheads, except we cut them out by hand instead of using a water jet cutter. We glued them to the foam, cut out the foam by hand, and sanded it down to a smooth shape. So for the, as seen in this picture here, it can be the sandwiches shown where we have the E-glass on each side and the foam in the center on both the bulkheads and longerons. When we glued everything together, microballoon epoxy was used along with E-glass overlays, as shown in this picture, to help strengthen the joints. So for the actual gauge locations, we had a total of 12 axial strain gauge attached to the right wing section only. They were attached between rib and 7. Rib 7 is the disconnect location. We have disconnect locations for our RFP requirement of fitting in a 3 foot by 3 foot by 6 box. The strain gauges themselves are located 2.5 inches to the right of rib 7. And then we had 6 strain gauges on the forward spar, 6 on the aft spar. There's 3 located on top and 3 located on the bottom. For the rosette strain gauge, we had the one rosette placed in between the 2 spars, which is 8.5 inches out to the leading edge and 1.5 inches up from the bottom. This was placed on rib 7, which is our disconnect location, and the wires ran straight down to a dashboard system. This image here shows the orientation of our strain gauge. To find the displacement, a fish wire potentiometer was used. They were placed at the wingtips on both the left and right side. The wire was wrapped around the wingtip and dropped straight down. We had some excess carbon fiber when we did our structural testing. We did not have time to get that cut off because we were pressed for time. So we did not assume that, they assumed that that would not affect our final results. So we left the excess carbon fiber on there. The fish wire ran around the wingtip and went straight down. The pump bob was used to make sure that the wire was straight down to get an accurate reading. So to apply the loads, we used the same load applications as described in Salvador Cardenas section for the ANSYS model. That way we can compare them at the end. They are all measured from the center line of the wing. And the load was also the same as in the Salvador's ANSYS model. And these were taken from ProRex load analysis, and it's 80% of the predicted load limit. We had a maximum load of 23.9 pounds applied to the wing. So as can be seen here, we used sandbags to fill up. We filled up little bags with sand to simulate the distributed load across the wing. The loads, the weight was shown in the last slide. We had the aircraft flipped upside down, as seen here. This is so that we could load the bottom side of the wing to simulate the lift distribution across the wing. The aircraft itself was placed on foam blocks and ratcheted to the table. And then loads were applied as evenly as possible to make sure that we did not rock the aircraft too much during loading. As can be seen in this picture, the dashboard system was right under the right wing, which was the only wing that had the strain gauges applied to them, and it went to the computer here. The computer was running the LabVIEW code as shown here that takes the Dacusness information and plugs it in and comes out with strain values. The values were then read into a Excel sheet, and from the Excel sheet we were able to plot our results. So for the results of our raw data, we had 2 strain gauges that failed. We had the strain gauges, the aft strain gauge that failed on both the top and the bottom. So on the spars we had 3 on top and 3 on bottom, and the one closest to the leading edge is leading, then the middle and aft. We have so the aft failed on both of those. And now we have consistent, we have similar data here for these two strains. And from solids and structures, we know that the strain should be equal and opposite on the bottom of it. So using that data, we concluded that the middle is the best data to use since it is similar to the top. So for the aft spar, we had similar. We have two strain gauges that compare, and these values were used to figure out what the bottom one was, since we have 3 different lines. The one gauge did fail, that's why it had shown a strain of 0. So from this, from the top, we found that the middle is the closest to the top, and from solids, we know that it should be equal and opposite. And then, so now I'm going to compare our results to ANSYS. As you can see here, we have a deflection of around 2 inches. Using fishwire potentiometer, this is what was found. In ANSYS, it was found that we are supposed to only have a deflection of 0.15 inches, as mentioned in Salvador Cardenas' section. We have these are the strain values compared to the actual, and as we can see, the actual is much less. It's actually 10 times less than the ANSYS predictions. I found out it's actually 10 times because I found that there was a gain problem, and I had originally a gain of 10, that it should have been 100, and the 100 brought it down, but when we had a gain of 10, they lined up. We are looking at our code to see if we missed another gain somewhere of 10 to bring, we missed another gain to bring the results back up. But we also have greater deflection than what was predicted. And we think that it wasn't that when we loaded it, it's not a perfect cantilever beam. So the loads across the spars were not the same as the ANSYS, which predicts the model that is perfectly cantilever beam and perfectly bonded. Here are the results for the aft spar. Again, we are much lower. For the shear, we are closer, but we are still under what ANSYS predicts, as can be seen here. So in conclusion, our strain and shear values are not quite matching up to our predicted ANSYS models. Could be due to several factors that in our ANSYS model. We used the layup. We used the information from the materials testing. The materials testing was for 4-ply. We only used a 2-ply layup, and we also think that the wing was not a perfect cantilever beam, which was modeled in ANSYS. So from flight testing, from the SDA, we want to go to flight testing the first with avionics needed to be installed, and Alex Gill will go over the avionics design.
So as Grace Brennan described in the beginning, that we have additional R&D requirements to install an avionics package in our aircraft, which is what I'll be talking about. I'll be talking about the capabilities that we have in order to meet the RFP requirements, as well as the components on board and on the ground to implement those capabilities, as well as testing. So the most obvious of the capabilities is the autonomous waypoint-based flight. We also have fail-safes, such as if the aircraft were to fly outside of a geographically defined fence, or if the aircraft were to fly out of range of the ground control station, that it would have a predefined failure mode and behavior. We also have telemetry, so that we can read data from the aircraft, such as where it is and how fast it's going, as well as the live onboard video feed. So these are all the onboard components. The components on the top are part of the autonomous flight package, and the bottom are simply for the FPV, the live video feed. So going down this list, first is the Ardu Pilot Mega. It is a primary flight computer and runs the Ardu Plane firmware. Next is GPS magnetometer. It's a single block unit that provides location and heading information. A pitot-static sensor for airspeed. It just included a dual pressure sensor, a pitot-static tube, and some additional pressure tubing. Telemetry radios, they operated on the 915 megahertz band and used a small duck-style antenna. And the avionics battery, it essentially powers everything except for the FPV equipment and the main motor. This image shows actually a number of the FPV components. The dark objects are actually components that go on board the aircraft, and this is something we'll see later. As it says, it's on the ground. The Minim OSD actually will display some of the telemetry data on the live video stream, 2.4 gigahertz transmitter, and the Sony FPV camera. And then this is the FPV battery to power the components in the previous slide. This image shows or gives you an idea of what the onboard connections are. This is essentially a cutoff line right here for all of the autonomous flight versus the FPV feed components. On the ground, a couple of these components are the same. The 3DR telemetry radio and the FPV battery I just covered a second ago. But for the, going down this list again, for the notebook PC, it was a simple Windows 10 notebook PC running the Mission Planner ground control software. We have an FPV monitor to display the camera feed, and then again here is the FPV receiver to receive the signal from the transmitter. Testing, we have only accomplished bench testing at this moment. We did establish a radio telemetry link so that the aircraft can transmit information wirelessly to the ground control station. We calibrated the sensors so the aircraft can know how fast it's flying and where it is. And last is the FPV feed was established. You can see what the Sony camera would be able to see. So we don't know, we may or may not continue testing depending on what happens the next week or so. But that's essentially all I've got at the moment for the aircraft, the avionics. So in conclusion, we have the capabilities, the components, and all the testing. With that, Hannah Warren will continue with what we accomplished in the flight testing.
Thank you, Alex. Today, I will be going over how we assembled our flight test article from our structural test article, which involved installing the internal fuselage components, installing the fuselage skins, creating the empennage and the landing gear, and then also discuss some of the issues that we encountered during this process. I'll also be assembling this flight test article, as well as writing the flight test plan and completing the structural test for part of our statement of work. However, we were striving for a flight test, which we did not accomplish, but that's not required under our SOW. The first step to completing our flight test article was to create the fuselage floor. This is created out of a floor-ply e-glass, which was then cut to the shape of our aircraft. And then we drilled holes for the landing gear attachment, as well as made a recess for our radios. And you can see how it was attached to the fuselage substructure here with e-glass overlays between the bulkheads and the floor to strengthen it. Here you can see a better picture of our aluminum doublers for our landing gear reinforcement. This is the main landing gear, and this is the nose landing gear with the bushing that was discussed in the fasten joint section. This is the layout of our fuselage components, most of which were just discussed by Alex Kill in the avionics section. If everything looks like it's kind of smashed in the front of the aircraft, that's because it is. We had some issues with weight and balance, and we shifted our components forward to try and correct that issue. You can see this is our motor, our electronic speed controller. We shifted our flight pack battery, which is our heaviest component, forward to the main landing gear, as well as our autopilot, our radios, our battery, servo, camera, pedostat tube, and our GPS magnetometer was never fully installed because we did not successfully fly. Next, we completed the aft section of our fuselage upsweep. We did this by making a foam form of the fuselage upsweep, laying up e-glass over it, and then pulling it off the form. You can see here it being applied to the fuselage substructure with strengthening e-glass overlays. We did have a few gaps between the longerons, the bottom longeron and the skin, so we made a chopped fiber e-glass epoxy mix to kind of fill that space. Unfortunately, that again added a little bit of weight to our aircraft. Next, we applied our fuselage skin. We did this by first applying it to the aircraft and putting an e-glass overlay over the cut that was made to pull it off the foam form earlier. After that was cured, we added foam fillets to both the underside of the wing, as well as to kind of smooth the transition from the fuselage to the leading edge of the wing, and those were then covered in e-glass. After that was done, we added an e-glass overlay to the mating of the fuselage skin and the fuselage upsweep. Once that was cured, we cut off most of the left side of the upsweep to create a large access panel to access both the internal fuselage components as well as the power plant components. And you can see here the aluminum brackets that we applied Velcro to attach that access panel. We created the nose of our aircraft by using a 7-inch styrofoam craft wall and laying up e-glass over that. After that was cured, we hollowed out the foam inside the nose. The entire nose is an access panel. It's good. It's an access panel. To create that, we put the nose dome in place and then applied release film to the fuselage skin and then used an e-glass overlay to overlap the skin and the nose cone so that it could slide on and off, and you can see it's attached also with Velcro. Next, we continue to create our empennage components. The first one we created was our horizontal tail. Our horizontal tail and vertical tail were completed in the same process to the wing, where we printed one-to-one drawings of our airfoils from our drawing package, cut out templates to hot wire the foam, as well as cut out our ribs, and then assembled the foam and the ribs onto pre-manufactured carbon fiber spars. After that was complete, then we wet lay-up e-glass over to create a skin. Here you can see some of the finishing process for the horizontal tail. You can see here the slit that was cut to create the elevator with the foam hollowed out, as well as the recessed servo. And the team member here is applying the pitch horn to actuate the elevator with the servo. Like I said, the vertical tail was created in a similar fashion with foam and ribs. Here you can see, again, the cut for the rudder, as well as the servos. And there's a little bit of an extension here on the right vertical tail to correct for some issues that we had assembling the empennage. We found when we decided to assemble the empennage, we created the tail booms out of 1.5-inch carbon fiber tubes with holes drilled to accept the spars to the horizontal and vertical tails. However, when we began to dry fit this into the aircraft, we found that somehow in the manufacturing process, the receptacles for the tail booms had gotten torqued, so it looks something like this. And so to make our horizontal tail level, we put it in place and used the level to make it sit in the right spot. And you can see in this picture, this bulge here is actually the spar for the horizontal tail on the right-hand side. And we cut just a little bit into the tail boom itself so that it would sit in the right place, and then use some more of the chopped e-glass epoxy mix to bridge some of the gap, and then use a 2-ply e-glass overlay to strengthen the joint. On the left side, it fit as we had planned, and on the left side, the horizontal tail center line and the tail boom are lined up, but you can see here on the right side that they are offset by quite a bit. So then we continue to assemble our empennage by applying our vertical tails. But to make the right-hand vertical tail sit level with the left hand, we had to apply a small foam piece underneath it. Originally, we had routed the servo wires internally. However, during the manufacturing process, the connection in the receptacle got damaged, so we had to end up routing those externally. Next, we moved on to making our landing gear. Again, we made one-to-one printouts from our drawing package and created a wooden form for our main landing gear and laid up 38 plies of carbon fiber over that. Once that was cured, we pulled it off and trimmed it. We put our wheels on and drilled holes to accept the hardware that would attach to the fuselage. Similarly, for the nose gear, we created foam forms and laid up the carbon fiber over them. Here you can see a picture of it assembled with the hardware holding the C-spring and the fork strut together, as well as the landing or the wheel installed and the threaded rod that attaches it to the fuselage floor. Here's how we attached the landing gear to the aircraft. This was discussed earlier in the fasten joint section. The threaded rod for the nose gear goes through a hole in the skin and through the floor and is attached by jam nuts. There's also an arm on the top of this threaded rod that is attached to the servo via wires so that we can actuate the nose gear. And here's a picture of how the main gear attaches through the fuselage floor. However, we decided to make the bolt head side inside the aircraft so the bolt head is against gravity. So once we had our tail assembled and we put it onto the aircraft, we realized we had some weight and balance issues because when we put the tail on, the aircraft tipped. And so that indicated that our center of gravity was actually aft of our mid-landing gear. So we started doing some investigation. We found that our tail was actually 5 times heavier than we had originally predicted. This may be due to some of the issues we had to correct the misalignment, but we also found that the wing was 3 times heavier than we had predicted, and the whole aircraft in general had gained some weight. So to remedy this, we shifted some of our internal fuselage components forward, as well as added 25 pounds of ballast to get it to sit level, which brought our complete weight up to 55 pounds, which is over our RFP requirement and at the limit for the FAA to consider us a small UAS. And even after doing all that, our CG was still about 12 inches aft of where we wanted it to be. Because of the extra weight of the ballast, we had some issue with the landing gear. You can see the gear was causing the fuselage floor to deform. So to kind of offset that, we put a steel plate underneath the nose landing gear. We picked a large, pretty thick steel plate to also help with the ballast. And for the main landing gear, we made an aluminum L bracket, which not only strengthened the floor, but prevented it from rotating back because it interfaced with the bulkhead. We also had some issues with power. We originally wanted a pretty powerful KDS motor, but we had some issues with that order and the motor never came in. And with the added weight, we needed more power. But since we have an engine that is mounted above the centerline of the fuselage, it creates a nose-down moment, and the amount of thrust that we needed to take off caused such a great nose-down moment that we did not have the tail authority to roll for takeoff, and even if we got off the ground, we would simply pitch forward in flight. So we made the final decision that we would not be able to flight test without some serious redesigns. You can see here, we still wanted a taxi test, so we borrowed an available E-Flight 90 motor supplied by the College of Engineering, which would be underpowered for flight, but was sufficient to get us to taxi. Next, I will go over our flight test procedures. First, I will give the phases of our flight test and the purpose of those, and then I will talk about the results. The purpose of our flight test was to verify our design. It was to be completed in accordance with the FAA, as well as the American Model Association and the Chino Valley Model Aviators, since they were gracious enough to donate their field. It was to be completed in 8 phases, 4 of which were pre-flight tests and 4 of which were flight tests. The pre-flight phase 1 was the assembly, which was just to verify that we could assemble it. The second phase was the controls phase, which is to verify that the controls are deflecting the proper amount with the RC receiver. The third phase was the propulsion phase, where we would verify our thrust as well as verify that our motor was throttling correctly. And the fourth phase was the avionics phase, where we verified the APM as well as the FPV camera feed. For the flight test phases, the first phase was taxi, which is to verify that we could achieve a controllable taxi. Phase 6 was takeoff and landing, to take off, land, and also to verify that we were basically controllable in flight. After that was complete, we would have went into a second flight test to investigate the stability of our aircraft in flight further by giving it control inputs and seeing how it reacted. And of course, phase 8 would have been fully automated autopilot flight, where the aircraft would take off under manual control and be switched over to the autopilot, where it would fly a pre-designated flight plan. We were able to complete some of the phases. We successfully completed the assembly phase. The controls phase was incomplete because we did not have an RC receiver available to us, and that's required for that phase. However, we were able to individually deflect each servo. The propulsion phase was a success. We were able to throttle our motor, and it did produce thrust. The avionics phase was incomplete, again, due to the availability of the RC receiver. However, we were able to verify that our FPV camera was transmitting and receiving feed. We did have some success with the taxi. We were able to taxi forward. However, because of the added weight, our nose gear collapsed after about 10 feet. We were not able to attempt any of the other phases because we were not able to successfully fly. In conclusion, I've discussed how we created our flight test article and our flight test procedures and the results of those flight tests. We had some issues with the weight and balance that prevented us from flight, but we did have some success with taxi. But we would have to do some serious reconsideration of our design and manufacturing process to continue flight testing. Next, Grace Brennan will discuss project management.
Thank you, Hannah. So first I'll begin by explaining our hours. We worked about 2,800 hours this semester. If we combine the hours we worked last semester in our preliminary design, that would be about 5,000 hours that we've put into building, or designing and building this aircraft. Here's our disbursement of our hours. We spent about 75% of our hours manufacturing and in class, and also in writing up reports and making this presentation for you. Here's our hours compared with previous classes. I would say that the reason we are so much higher is that we did have a lot of manufacturing issues, which meant we had to spend more time either going back and redoing stuff or fixing stuff that was already made. And here we have our budget. We are actually well under our budget. This was because the motor that we had planned on buying ended up not coming, so we got refunded for that, as well as we did buy another motor, but it wouldn't fit with our aircraft, so we had to return that one as well. And we ended up using a different motor, which is down here. So our combined, our budget was $2,000, but we only ended up using $1,500 of it. However, with the material and all the epoxy that we ended up using, we would have been well over our budget. We also got an additional budget for our avionics. That budget was $500. However, since most of the stuff was available to us to use, we were still about $200 under budget. So for our budget, we were pretty good. Some of our future tasks would be to do more avionics testing. We did a basic bench test. We weren't able to connect all of our components up. So something that we could do is make sure that all of our control surfaces are connected to the actual system in there. Additionally, we were discussing redoing our taxi tests. As you can see on the actual flight test article, we tried to reinforce the rod with nuts. However, that wasn't quite successful. So what we would probably do would be get double the size of the rod to help reinforce it and allow it to carry the extra load that we had to put into the nose gear. So in conclusion, obviously one of our biggest issue was our center of gravity. Because it was so far off and we were unable to really fix it, we were unable to fly. This happened because, as mentioned, our wing is 3 times the weight predicted, and our tail gear was 5 times as predicted. And because the tail gear is so far away from where the main body is, that moment arm really created this center of gravity to be off. What we could have done to fix this would have been to redo our estimations after material testing and weighing the materials. And it wouldn't be a great estimate, but it would be better than just trying to guess from what we had. Additionally, we should have been more careful while laying our epoxy, because several parts of our aircraft are very epoxy heavy. And additionally with that, we should have been weighing our parts as we put them on we would have noticed that the center of gravity was going to be off using our predictions. That kind of goes into one of our other issues. We had a lot of manufacturing issues, which just caused us to be pushing our deadline for flight testing farther back. If we had been able to notice that our center of gravity was off sooner, we might have been able to do more to fix it. What we could have done for that was really scheduling, be a more precise schedule, and we should have set deadlines for individual components instead of just, we want a flight test by this date. Additionally, we had lots of material. We ran out of epoxy at one point, we ran out of e-glass. So one thing we should have done is make sure that we have all the necessary materials before we started manufacturing our parts. And finally, another way to fix that was we assigned tasks to certain individuals so that we didn't have 5 people working on one part at different times, so that things weren't communicated correctly. To conclude, I would like to thank Professor Heldling and Dr. Beck for being a great help and a great place for advice and knowledge. I also like to thank Mr. Patrick David and Mr. Danny Krauser for their help in the machine shop. I would also like to thank Jim Weber and Mrs. Chalet Mogford for their help getting us all our parts when we needed them. I'd also like to thank Nicholas Kearney, our pilot, and Chino Model Aviators for allowing us use of their facility. I'd also like to thank all the teachers who helped us with several of our calculations for our design. Dr. Bordion, Dr. Mosier, Dr. Schraub, Professor Swick, and Dr. Lanning. And I'd also like to thank you panelists for taking time out of your schedule to come listen to us today. And now I'd like to open the floor for questions. Speak really loud.
All right, everyone done? Yeah. All right, so as you guys probably heard, my name is Connor Warren. I graduated last May. I'm currently doing mechanical engineering work, doing CAD, and I used to do T&E work not too long ago. So, sounds like you guys had a rough project. But it does seem like you guys learned a lot from this project. And I just want to say that because I think you tend to gain more from your failures than from your successes. So I just hope you guys make the most out of this. And with that, let's jump right in. Hopefully this won't be too bad. One quick question I have about your ANSYS model. I know you said it has issues. I know you said it's wrong. Now, if you were to correct it, where would you start?
Probably we would do materials testing for the actual carbon fiber tubes, because those are just taken from the manufacturer.
Okay.
We would also do the exact layers that we used on the actual structural test article, and then probably, yeah, that's probably what I would do differently, and then make sure to do hand calculations to make sure that matches with all the properties we use to do a sanity check.
Okay, were the specs off for those tubes, or?
They were just taken from the Clearwater, but you can never really trust the manufacturer, so.
So yes, they're off.
Right.
Okay. Okay. All right. And I guess the other question, are we still on the 2-question limit?
One.
Okay. So yes. Okay. For your wing loading test, why did you load both wings? I don't know. You don't normally see that, so I'm a little curious why you loaded both wings.
We loaded both wings so that it wouldn't tip over or favor one side, so when we had them both on there, the potentiometer would measure the deflection as if it was flying.
Okay. So is it easier to strap it down that way?
Yeah, we made our first fuselage, we realized it had some problems, so we still used it so we could strap it down without damaging our bulkheads.
Okay. Just most of the time the way I've seen it done is you strap it rigidly to like a table or something, and then you only load one wing. So I was just curious because I hadn't seen it before, but as I've said before, I'm not an astro guy. Or I'm not an air guy, sorry. Anyways, hope you guys make the most of it. Good job.
Thank you.
All right, guys, good job. You guys had a tough RFP, so that's all right. At least you guys learned a lot, that's for sure. A couple little things. You guys had good use of your charts and stuff. Thought they were pretty good. I thought that when you guys were talking about manufacturing, you could have showed more pictures because you kind of talked about a lot of stuff you did, and you only highlighted a few things in images that have been useful. You know, I know what you guys did, but most other people here don't. So.
Well, to that, a lot of times, like, we would forget while we're manufacturing because we get so wrapped up in it. And
I know. I remember that. So, I mean, that was just one thing that I thought. I had a couple questions. Another comment. It's not a question. It doesn't count. So. So you might want to look at what your customer is, because you guys mentioned Windows 10 was your operating system. I'm pretty sure that Coast Guard is not on Windows 10. So as a government, we're going to handle that type of stuff. Just so you guys know. Just got to keep those things in mind. That stuff. I'll just ask you one question right off the bat. So if you were to sell this to a customer, what would be your plan of attack from here, essentially?
I think our first plan of attack would be to go back to kind of the preliminary design phase and re-estimate using what we have here, basically. Like, probably have to move the wingspan forward. But there'd be a lot of work involved.
That's fair.
Oh, Jacob has
Yeah.
Well, more comments on that. One thing is we could better, we could use our CATIA model using with our new found weights. We can get better densities and better, get a better weight and balance calculation than we did in the preliminary design. Get it more accurate, and then we can start looking at possibly, reducing our core length of our horizontal and vertical tails, because that will reduce the weight. We can also look at reducing the boom diameters of our empennage. We can look and see some other, how much more we can reduce on the wing as well, try to reduce that. And then I would also extend the fuselage a little bit farther forward so we can put a little more ballast there. So it's probably our camera will be able to aim forward.
I would also like to, I don't need that microphone, I was just saying, one of the biggest things that could correct our weight and balance problem is in our original aircraft, we have almost 10 pounds of batteries, which is located in the aft of the fuselage. So if we moved our components around, we could put our battery in the nose and correct a lot of our problems.
Yeah, that's fair. I mean, when you haven't done most of the stuff before too, so it's really easy to use way too much epoxy. So I understand. So I just had it too. I just had another question. That sucks. Fantastic. Good job. I'm gonna go with that. That's
We'll take that one.
Yeah, good job. I know it's tough when you can't get to the place you want to and things go wrong. I'm going to ask you a few rhetorical questions that I don't want you to answer. If you could bring up the slide 56. You mentioned you had two different data about the carbon fiber that you got, and you kind of just chose one. Don't answer anything. You didn't really explain, why you chose it or go into depth. Don't talk about it.
I won't comment.
Yeah. And then in 59, slide 59, I guess 58 too, how the data kind of skips. That I don't think that was really explained. You kind of just blew through that, which leads to my question. In comparison with your ANSYS model, I think the goal of this project is not necessarily a flight test. That's why it's not required. It's to do engineering work, have predictions, and try to make the vehicle match the predictions. So I think your conclusions were weak. At the end, I think he just moved right into flight test and kind of breezed through that. And you didn't explain, you didn't really go into depth about the differences that would have been or could have been or were, and even why you used 2-ply instead of 4-ply. That I think you said it was in your ANSYS model, and so that could be a big difference. I guess that's not really a question.
Well, what he was saying by, so we only did material testing for 2-ply. In the ANSYS model was modeled for 2-ply, wasn't it?
No, the material testing was 4-ply.
No, I'm saying in the ANSYS testing.
The ANSYS used 2-ply, and the
But-
material testing was 4-ply.
But we used the material properties from the 4-ply.
Right.
We didn't have material properties for a 2-ply.
Okay.
So that's what he was saying by that.
That's in the actual structural test, we used 2-ply wing ribs. For the material testing, and the values we used for material testing was 4-ply, and that's what we used in ANSYS.
Guess I have nothing.
So my comment was the same to the other team. It would have been nice to see what you guys meant and didn't mean for the RFP at the end of the presentation. That was it.
All right, excellent job, guys. And again, when I did it, I didn't have to fly something, so it was just simply build and test. So having the flying component is an extra critical constraint. So slide 12, you're talking about your CL alpha curve. guys said you predicted a stall at 13 degrees alpha, and you measured 10 degrees. I'm not seeing your stall with your tail on. And if I look at your tail off, your stall angle is a little bit higher than 10 degrees. So why the variation?
Well, at that point, the reason that during wind tunnel testing, there was a lot of model variation. You could see stall in the wind tunnel. You could see it rocking back and forth, and we didn't want to continue, otherwise we would damage the pyramidal balance. So you could really see it shake with the large model in the wind tunnel. So
How big, which tunnel did you guys use?
we used a large closed circuit wind tunnel. I don't have the exact dimensions.
It's 36 by 36, right?
Yeah, something like that.
A person could fit in there, that's all I can say. We won't reminisce about my college days.
So I should have clarified that stall was done. That stall point was done by visual inspection of the wind tunnel model in the test.
You said it was done by, okay, so
Because you can see the model rock back and forth quite.
you're using test then to validate your stall, or you're using
No,
the
it's
force?
the actual model itself. It was rocking back and forth, so that was an indication of stall. And we didn't want to proceed forward to ruin, otherwise we'd ruin the pyramidal balance that we were
Okay,
attached
so you're
to.
using buffeting as the
Yes,
vehicle.
buffeting.
Just curious, all right. I think I have a couple more questions, but I'll have to be selective here. Just a couple observations. On slide 150, when you guys talked about displacement, you guys used scientific digits. Usually you can just kind of get away with just a number value, especially since your deflection was relatively small. Just observation.
He's saying we should put it on.
Oh, okay.
It was just an observation.
What
so
point
we
on
could
the
say-
span is deflecting, is the point.
So that was one of them. Let's talk about your landing gear system. Both your team and the previous team used composites to fab up your main landing gear and nose landing gear. And composites is fun, sometimes to work with, sometimes not so fun. Why did you guys use composites in lieu of, say, sheet metal, where you could simply make a standard bend? It's there, you have material properties already, it's quick, it's easy, it's done. You make your cuts. Why the option of composite versus sheet metal?
I believe the reason we used composites was because of weight. I think for the strength that we needed, I think it was lighter to create it out of composites instead of a sheet metal.
Okay.
Although with this many plies, it still has some weight to it.
I'll say your trade-off probably isn't that much of gain for weight, given how many plies you have, especially with the wet layup sequencing. So, just something to consider. Composites is nice, but you don't necessarily have this exponential gain with a weight reduction. It's a lot less drastic than people may think. So, but overall, good job. What I do like, I think you guys had a lot of good lessons learned. You summed up your lessons in terms of constraints, identifying critical paths very well. I think that's something that is very realistic that's out there. People see this big project and fail to realize that you can't get to the end without taking steps 2 and 3 in between. So very good identification of key tasks and constraints. But good job, guys. Congratulations.
Yes, thank you very much. A couple very quick ones. Slide 58, we're looking at that before. 58. Position, I assume that's the amount that something is being displaced. 200 inches, that's about 10 to 15 feet. What is that?
Yeah.
I believe that actually has the wrong scale on it, because that's not correct.
That's a couple of taller, he's standing in each other.
Yeah.
shoulders there.
It was supposed to be position of the crosshead of the actual tester, and I don't know why that is so off.
Could it also, could it be strained?
The slide just before that, 55. Looking at Poisson ratio here before. On a vertical scale, I see negative Poisson ratio.
Right.
Giving me over here a positive. What's going on there?
Right, for the Poisson ratio that's highlighted, we took the absolute value. We forgot to take the absolute value on the plot, that's why.
Well, it should be positive. But why did you get a negative to begin with?
I think what he means to say is that we forgot to take the absolute value of the,
Grace, no. One of the reasons it might be negative is because these strain gauges sometimes give you a negative value when you do not have a negative value. They don't really give a reliable sign, and we use the sign that came off of the strain gauge. So we should have altered that.
Sort of curious about that. If you go to the slide before that, 54, there is the possibility. So you've got this specimen in there. It's kind of on the wide side. It's not all in the grips there, so you're bending it. And where there's the possibility you are actually, depends where the axial strain gauge is there. I kind of doubt it, but maybe it actually is expanding because you've got some compression. You're bending in there. It's sort of in the middle. I kind of doubt it there, but we're not sure. That specimen is too large. We're getting bending, so results are suspect.
We didn't consider that.
Poisson should be negative if you're just taking the strains directly because of the compression. You have compression. When you're expanding, you're compressing in the perpendicular direction.
It's stretching on one side and pressing on the other, more or less in the middle, but usually odd. Maybe you actually did calculate correctly. You're getting a negative. Probably. Now, last thing on the ANSYS model. So your one ANSYS model was with the skin on there, and then you were showing it with the skin removed just to show the strain gauge location.
Right.
Correct. The mesh on those tubes was awfully crude. Slide 121, for instance, and we worried about the results from that kind of mesh. Got the holes and so forth as to where pins and stuff like that go. So maybe you've got a little bit better job modeling done there. Last question on the mesh. Do you include the break in the skin?
Yes, that's
there,
included.
so-
That was modeling a TN, that was included with ANSYS model.
Okay, so when you finally look at your results, last slide there, Jacob, you were looking at these towards the end, you have this big difference. So for instance, slide 151, between ANSYS and ANSYS and
The strain
what you've
gauges.
got here. Which ones do you believe more?
Probably believe the actual structural testing more, just because we tested it. But
Well, additionally, because like you said, the wings do
why
weigh,
the big difference?
the wings do weigh three
Oh.
times as much as they were, which
one
would change.
One thing we came up with is since it wasn't perfectly strapped down and it could rock, that location doesn't feel all of the strain, but in the actual ANSYS model, it's perfectly fixed there, so that location will get more, it'll experience more strain than the actual structural test because it's rocking a bit.
When you were talking about the results, Jacob, I think you were making reference to solid mechanics helping you to inform some of the correctness of the results. What does solid mechanics tell you about these values here at the strings?
You're referencing timber. Timber talks about the section.
Oh, it's timber, okay. All right. What does solid mechanics tell you about ANSYS versus the actual, you've got actual strain gauge readings, but are there a problem with them or what? I'm not really sure. Somebody used beam bending analysis in the original sizing of tubes and stuff like that. If you apply it here, look at these strains.
I did not apply the bending that they had calculated. I put on this at the last minute to calculate all the.
That would be a great thing, and I think maybe for the first group also, I didn't hear reference to that. Solids is, here's some current solids, yes. Teacher, apply those things. Look at tip displacement, stresses. This is an effective beam, and it may be a little simplification. You can get some good results. That's what it's there for.
Okay, Wally, we'll give you one.
You
Already over time.
I know.
It does not take
What was
long.
these guys for?
It does not take a long time. I once had a group say, we didn't have time to do that, and I had done it there in 5 minutes, and I gave them the result. It was not good. All right, that's it. That's enough of that. Thank you very well. Looks like that's one thing.
Thank you. A couple of brief comments. One, I agree with what Professor Lang just said. Good news, love the figures. CFR 14, part 23, it's just a detail. Where are you, Phil? And try to keep your units consistent, inch pounds and foot pounds, pick one, report the same. Okay, yeah, your wings were heavier, therefore your actual deflection should have been greater than your ANSYS model. Right?
Yeah.
Does that make sense? I mean, that's just a quick common sense. Do I believe my model or not? And because being a computationalist, I have to go back to the measure refinement. What, if any, measure refinement study was done? The answer, I'm going to predict, it was none. We meshed it once, ran it, and said that was the result. Okay? No bueno. All right. Now, I'm an ERAU person too, so let me ask you an ERAU question. I noticed when looking at your model that, okay, you guys aren't perfect manufacturers. First time, fine. I'm not judging, observing. Okay? So we have a lot of extra material, especially on the upper surface, especially near the forward part of the wing. What might that do to your lift characteristics? You now effectively have a higher cambered, thicker wing.
So you're saying we changed the shape of the airfoil?
You change the shape of the airfoil, and therefore you're going to have a lower stall angle with a higher lift coefficient.
Yeah.
I actually think I remember, because we painted our wind tunnel model as well after it had already been manufactured. And I think I remember someone, was it Professor Hoping?
What?
I remember a teacher told us that we should, oh no, it was Danny Clauser.
Yeah.
He told us we should remeasure our airfoil and account for the changes in our predictions.
Yeah,
So yes, that would change.
Is your geometry consistent? Is your physical geometry consistent with your calculated geometry? Which has been a consistent all the way through here. By the way, again, hard questions, but this is the environment where you get to be off by 500%. It's okay.
Can I actually ask you a question?
Sure.
So what would we have done differently in the manufacturing to account for that?
Oh, sorry, wrong guy. Jim? Can I, one more? Okay, thanks. Sorry, got too close. Okay, configuration. Who is responsible for configuration?
Actually, several. Or you mean the manufacturing or
No, the initial
several of us.
configuration,
I was in charge of fuselage configuration.
I was doing wing configuration.
And
Okay, so did we know at the outset that a thrust line above the center of gravity would cause a nose down moment?
We did know that, and we had to do significant resizing of the tail in the initial phase. However,
Was 500% enough?
No, but we did make it big enough to make this aircraft fly, but we did make sure it was big enough to make our preliminary design aircraft fly.
Okay, and yes or no, is the aircraft overweight due to manufacturing or due to design? I'm sorry, it's not.
I believe it's a bit of. I
manufacturing.
believe it's a bit of both. I think we did use too much epoxy in our manufacturing, but I think it still would have. We predicted our vertical tail would be 1 pound, and that now that looking back, that seems highly unrealistic.
The prediction was the entire empennage was 1 pound, not the vertical tail.
Sorry, that's it.
I'm satisfied.
Okay, thank you.
Thank you.
We would also like to thank our secret panelists. Thank you.